Okay, previous class we discussed about this tutorial question, and we stopped in a midway. Okay, so just to recap what have been discussed, we're having a system like this. So we are pumping from tank number 1 using a pump, and then the water will reach tank number 2 at a higher place. So the elevation or the Z differences between 0.1 and 0.2, which is the water level here, is 10 feet. Again, for this exercise, ignore the imperial unit. Try to pay attention on the method or the approach that we use. Okay, and you're having the KL value. Again, when you're seeing the KL value, means that this one is for minor losses. Okay, to calculate minor losses, you will see this one in your tomorrow test also. Okay, so KL is for minor losses, and yeah, all right, then you're given the diameter of pipe and also the total pipe length and so on. All right, and then for this tutorial question, you're given a chart there. So on your screen, you are seeing the efficiency versus the Q, volume flow rate, and these two lines are given by the manufacturer. Okay, by the manufacturer. They will be give you the efficiency chart and the head. So you need to use this efficiency versus Q chart to solve this question, right? And we have discussed that we will use this equation, energy equation, to solve all the pipe question with a pump. So on the left hand side, you're having the pressure, velocity, elevation, and the actual head loss. Actual head, so not loss, actual head. And the right hand side, you have the pressure, velocity, elevation, and the major head loss and minor head loss. So just to remind yourself, this is pressure effect, energy. This is velocity, because this one will give you, this one is hydrostatic pressure energy. This one is the kinetic energy. If the fluid is moving, then you're having a kinetic energy. So you're having a V effect. This is a potential energy due to the height, due to the Z elevation. This is the actual head. Okay, actual head. Not head loss, it's the actual head. What mean by actual head? Just to remind yourself, if you're having a straight pipe and you go through a water and you put in the capillary tube just above the pipe, and you'll be seeing water level going up in this capillary here. So this is the actual head. This is the HA. Okay, so this is the HA. So you put in the actual head on the left hand side of the equation. Then after that, on the right hand side, same, you still have you need to equal what is in and out. The energy must be balanced. So on the right hand side also have pressure effect, energy, and also the velocity effect due to the kinetic energy. This one also elevation part point at number 2. Then this one, FL divided by dV squared divided by 2G. This one is major losses. Okay, major losses. So what mean by major losses? Major losses is due to the very long pipe, and there's a friction within inside the pipe. So this is the major head loss. And this F here, you need to use Moody chart to find the F. Okay, Moody chart. This F value is straight from the chart. Straight from the chart. Okay, after you get the Reynolds number, after you get the Reynolds number, after you get the surface roughness divided by D value, intersect of these two, go into the line, and then project to the left, you get the friction on the left hand side. So this is the Moody chart to get the major losses. Then followed by, you see the KL. KL means this whole thing is minor head loss. Sorry, minor losses, not head. Minor losses because of all these bending. Okay, all this mending and opening and so on. Okay, so you have to differentiate what is major, what is minor. Right, so this is a very important equation when you want to solve pipe problems. Okay, yeah, so right. So when it comes to final exam, some question ask you to ignore major losses. So you just write out this equation, cancel this component and continue with the calculation, right? And so on. If the question asks you to ignore minor, then you ignore this one, continue calculation, and so on. Okay. All right. Then we also discussed why P1 equals 0, P2 equal to 0 means pressure at here. We are using gauges, gauge, pressure gauge here, P-A-U-G-E or G-A-G-E. Pressure gauge means you hold a sensor over here, a pressure sensor, you'll be reading 0 at the surface. Here also same. You put a sensor over here at the surface of the water, you will not get reading because it's exposed to atmospheric pressure. And also, we assume that we are having a large surfaces. Okay, regarding the pressure, as long as the surface exposed to atmospheric, we will get 0 for the gauge pressure. All right, and then for the velocity, why 0? Why this velocity at this point is 0? I think I explained to Raj last lecture, correct? Raj or Dinesh? About the velocity at this point by using the large tank. Is it Raj?
Yes, sir. Yes.
Okay. So remember, if you're having a large tank, the velocity at this point and this point is 0 because if you put your eye over here and look at the water level will go down very, very slow because of very large surfaces. So since it goes down very, very slow, you calculate velocity by using distance divided by time. So the distance moved by the water level is very small. So you can assume velocity is very equal to 0. All right. And then the delta Z here is quite direct. You measure 0.2 to 0.1 water level. Friction is given. This one F. In this case, I will just this tutorial question. I will just jump. I will just keep the Moody chart procedure. I will just give you the F value 0.02. Okay, diameter given, length is given. So you manage to find what is your major losses. Okay, major losses. While for the minor, you need to combine the KL times the velocity and V2. Okay, and previous class, I also mentioned there's a differences between this velocity and this velocity. V sub 1 and V2 is different from velocity in the major and minor losses equation. These two is inside the pipe, velocity inside the pipe. Okay, so straight away, you know that you want to calculate the velocity inside the pipe. For this chapter, I think since the first chapter 1, we already introduced you the Q. Q is a very famous parameter for this module or fluid mechanics. Q equal to VA. Q is given. Okay, Q normally will be given. Area you can calculate from the pipe diameter. Okay, so it will contribute you to A. And again, you are seeing a circle area. Circle area pi r squared. Or if you want to use diameter, pi d squared divided by 4. Then you rewrite this equation, you get the velocity. And velocity, the value you can share among major and minor, same V, okay? Because we assume the Q inside system is the same. And also, yeah, so V1, V2, this one is on the reference point itself. So once you get the idea of all the parameter, the rest is just substitution. Huh? So you just cancel the equation over here, and it will simplify to this form. The rest is just substitution. So I do the calculation for you over here, and you'll get equation in term of Q. So you have two equation. One Q is in the feet cube over second, and one is gallon per minute. Okay. So if you're using unit SI, then different constant value in front of Q. Okay. But anyway, the idea is to show you that you can put your HA in term of Q and parameter. So this one actually give you y equal to ax squared plus bx plus c equation that allow you to plot. This is your HA. This is your Q. So it manage you to plot HA versus Q. So you will get a polynomial graph by rearranging the equation from the energy equation just now. Okay, so this one later you need to plot inside the manufacturer graph. This one. Okay. Now previously we stopped at here. So if you watch carefully on your screen, you're having a chart which give you the HA, which is the head, actual head versus Q. Right, and you're having these two lines given by manufacturer. So you need to plot this graph in Q in a gallon per minute because the graph is in gallon per minute. So you plot this graph will give you this line. Okay, so this red color line is according to this equation. All right, we call it system curve. Okay, we call it system curve. This red line system curve. And if you combine side by side, on the right hand side graph is actually the same graph, but it just show you some important parameter. So just remind that this efficiency, this one, is actually there's a line here. Okay, there's a line like that. But it's just to have a proper explanation. The textbook, it removed this dotted line here. All right. So if you compare side by side, you will get an intersection of the system curve. This one, you'll get an intersection of system curve between system curve. This is your system curve that you derive from the energy equation. This is the system curve, right? So there's an intersection with your head. This line is from the manufacturer. So if you project down like what you see on your screen on the left hand side graph, if you project this one down, you will get your Q is 1600 gallon per minute, and you project to the left, you will get your head is 66.5 feet. Okay, and you project up this line from the dot itself, you will hit an efficiency line, and you project to the left, you will get the value of efficiency that produced by the pump. Okay, so in this case, you will get 84%. You will get 84% here. Okay, now the idea is from the intersection of this system curve that you plot from this equation, and then get the intersection, project down, project left, project top, go up, go down, go left. Then you will get the value of the pipe. This graph is referring to pipe, the pipe that you're using. Sorry, not pipe, the pump that you're using. Any question on these slides? Raj, able to capture? Let me, okay, Dinesh not yet here. Okay, Raj, are you there?
Yes, sir.
Yeah, any question on these slides?
No, sir.
Okay, good. Cool. Cool, you understand how you get 84%?
Not very sure. Can you say again for that?
Okay, so before that, do you understand how you get the red color line? Do you know how to get this line?
From the HA, right?
Yeah, from the equation. Then you plot lah. You plot using a graph. You plot, get this line. So when you get this line, the red color will intersect with the manufacturer data, which is given by this solid line head here. Okay, solid line here. The next steps, what you do from this point, you project down. What you get? Parameter, cool. You project down this one, what you get?
1,600.
Yeah, what is this? What is this? What is this parameter? You project down, what you get? Yeah.
Gallon per minute.
What is that? Is a volume. What? Gallon per minute is what? Or meter cube per minute is what? What do we call this one? It's like you communicate with the technician. You won't tell your technician in meter over meter cube over minute, right? So what is the name for this one?
Volume.
Volume what? Volume is this one, right? Volume in meter cube, but when you take volume divided by time, what do you get? You take volume divided by time, what do you get? Volume what? Volume flow rate. Okay. So Q, you project down, you get this one. Then after that, you project to the left. What you get? What you get?
60% efficiency.
No. This point is hitting what line? Headline, right?
Yeah.
So you are following, you're actually hitting the head. So you project to the left. Project to the left, you get 66.5. So the left-hand side axis, you're actually having two things here. This axis it represents two things. One is HA, one is efficiency. That's why you're seeing two solid line here. So when the red line cross the solid line, you need to see what line that you're crossing. One line is for efficiency, one line is for head. So this point, the red line is crossing efficiency line or head line. Cool.
Headline.
So you project to the left, you read the head value. HA, 66.5. Then I'm asking you how to get at 84, right? So
Yeah.
you project up. From this point, you project up, you hit a point. This point is intersect with what line? Head or efficiency line?
Head also.
You go up and you touch this line. This is what line? What is this line?
Head.
Cool, you understand the arrow meaning or not?
Yeah.
You understand this graph or not? Look at this graph. What is this line mean? This is head or efficiency, this line.
This one is head.
Then this one is what?
Efficiency.
Efficiency. Then back to the question I asked you just now. So this point go up, hit what line?
Or Efficiency.
Ah.
Efficiency.
So once you hit efficiency, you project to the left. What reading you're reading? You're reading head or efficiency?
Efficiency, right?
Because you are what? You are touching efficiency line. So the value you're touching actually is efficiency. That's why 84 value that you project from the efficiency line, it read 84% efficiency. If the point touch head, then it reading as head. You understand now?
Yeah, now I understand.
Okay, good. Okay. Now you understand about this graph. You know that this pump is maximum can produce at 84%. Maximum efficiency by the pump is 84%. So if the final exam, it will ask you if the efficiency in the industry or by the auditor, your factory must produce 90%. Does this pump suitable for the operation? The answer is no, because from this graph itself, it tells you the maximum pump that it can go is 84%. Okay, all the answer is from the line that you plot from the system curve. From the system curve. How you get the system curve again? From the energy equation that you derive. Okay, you plot this curve. After that, you look at the intersection of the curve. You hit the headline first. Read the headline. Move to the left. Move down. Move left. Move up. You get 1 point. Move to the left. You get efficiency. Move this lower point. You move to the left. You get heat. Okay. Don't confuse. Don't go overshoot and then say this one is your reference point. No. We are looking at this point and not this point. All right. Let's move on. So how to calculate power? Very straightforward. You use this equation. Power equation is power is capital W dot equal to specific weight Q HA divided by efficiency. This one from graph, you read just now, efficiency. This one from table. This one you calculate. This one also from graph. This one also from graph. Q 16,000. HA just now 8 point something. All right. Then you calculate now. Okay. Important when you calculate power, remember to have the same unit. In this case, you're seeing imperial again. When you solve the question, make sure you have the same unit. Okay. You'll be seeing imperial unit, not imperial, unit SI unit. Then after that, you can put either power in watt unit SI, and then you can convert to horsepower. Okay, this is power unit. Very straightforward. This slide actually showing how you apply this one from the chart itself. Okay, yeah. So the next one is that it just show you what happened if you adjust the Z, how you play around with this operation chart. Is that what happened if you readjust this Z? What happened you adjust this 10 feet into maybe lower or higher? How will you plot this chart? It's the same. You redo the same using this equation. You are adjusting this value. The rest is the same. Adjusting this value, you'll get the new equation. You'll get a new equation. If you're adjusting the Z, you'll get a new equation. This is the system curve equation. So you just use this new equation, plot into a manufacturer graph with the efficiency and head, can move out or move down depending on your Z value. Okay. So this slide is just show you what happens if you move delta Z is 80 feet and 100 feet. What will happen? So on this graph, this red color is the one that I show you. This is the system curve that we solved just now. And then if you plot the graph with a different Z, you will get two more graph on the operator graph, on the manufacturer graph. So one is for 80, one is for 100 feet. So you're having a two chart here. So again, if you read again this chart, just now the system curve that we plot is this one. Then what about 80 feet? So 80 feet will focus on the head itself. Okay, the procedure is that once you plot the system curve will intersect the head first. This is the head line. Will intersect the head, then you project down. Project down, you get Q. Project left, you get head. And the next one, you want to get efficiency. If you go up, you didn't see efficiency, so you go down to find the intersect of the efficiency line. So in this case, you get 36%. You project down from this point. Then you read to the left, you get 36%. All right. So if you can see here, if you increase from 10 feet Z to 80 feet, what happened to the efficiency? The efficiency dropped from 84% to 36%. Are you able to see this one? Cool, you able to see what happened if you increase the height between 2 points? The 10 feet that you plot just now, and then the one that is 80 feet by this red color line. Can you see the dropping of the efficiency? Just now you get 84%. Now you get 36%. Do you see the value?
Yeah.
Okay. Raj, you able to understand, right?
Yes, sir.
Okay. Shirley, you able to get it right?
Yes, sir.
Okay, good. Okay, now we solve for the 10 feet and 80 feet. So another scenario is 100 feet. So what happens if you have 100 feet? Your line will go up a little bit. However, if you see the line 100 feet, this one, let me erase. So if you have 100 feet, you are getting this red color line. So red color line, do you see any intersection of the head line? The answer is no. Okay, in 100 feet, the line doesn't cross any head line. It means this one, the pump is not operating. There's no pressure difference there's no enough pressure for the pump to operate. So if your graph, you plot the graph, and the system curve doesn't cross over the head, then it means this height is not possible. The pump will not working. Cool, you get it?
Yeah.
Right. So again, I just recap the procedure. If you want to use the manufacturer graph, so before you solving this question, you need to get a graph with HA and efficiency and a Q. So on the manufacturer graph, you are seeing two lines. One is the head line, one is the efficiency line. You're seeing these two lines. Okay, sorry, I'm plotting the wrong one. Let me erase this one. Okay, so you will get HA and efficiency line. So efficiency line like this. So you're seeing a curve like that. Next, the procedure is standard. What you do next, you calculate the system curve equation by using energy equation. You get something plus something Q square. You get this equation. Then you go to the manufacturing graph. You plot this HA graph. Okay, you plot this HA graph. Then after that, you from the intersection, this HA graph must cross the head graph. It must cross the head graph, not graph, head line. This line, all right, must cross this head line. If do not cross, means the pump doesn't working. Okay, so the step is plot the graph from the energy equation. It becomes system curve. Plot this system curve inside the manufacturing graph. You get the red color line. And this color line will cross the head. From the head itself, project down, you get your Q. From the line itself, because this red color line cross the head line, so you project to the left, you are reading head value, HA. After that, from this point, you project up. You are touching the efficiency line. So efficiency line, you project to the left, you get efficiency of the pump. Okay, so this is the procedure when you use the manufacturer graph to access the pump performance. Standard. Okay, yeah. The challenges here is that not all pump manufacturer will give you this chart. You need to really you need to be the end user of the pump. Then they will provide you the handbook. Then from there you will get this graph. Okay, normal user, they won't give you this one. You can only find in the technical handbook, maintenance handbook. Okay. All right, so we're done with this one and already explained about the 100 feet and 80 feet scenario and so on. So these are the procedure that we do. And nowadays we have computer, so all these graphs are inside design, are inside the analysis system. So if you work in a company later that work with a pump, so normally the pump supplier will give you a software that you can plot the graph like what you see today. Okay, you just need to key in the parameter of the system. Then the system will plot the graph, will give you all the answers straight away. Okay, let me watch the time. Okay, the next one, we want to introduce you a new parameter that you learned today. We call it specific speed. It's a dimensionless parameter. So this dimensionless parameter is to calculate the speed for the pump. Okay, so this speed given you this equation: Q volume flow rate, omega rotational speed. Yeah, omega is rotational speed. Rotational speed. Okay, because later you're going to graduate as an engineer. You need to be firm of the parameter that you use in your calculation. Okay, it's very bad if you're not able to communicate with your colleagues later on, right? So omega is the rotational speed, D is the diameter of the pipe, G gravitational force, HA is the actual head in the system, omega rotational speed, and so on. Okay, so the rest is quite straightforward as you see on the screen. I will not go through the derivation of this equation. I just straight away give you the equation. However, if you are lucky, you go to United States to work, they will use imperial unit where in terms of RPM. okay, in terms of RPM. So this is just touch and go, just give you some info. The above one is dimensionless. However, when you go to United States, they will use a dimensional form, mean with a unit. So they will call specific heat, specific speed with the unit. So this is the equation they use in the United States to calculate the specific speed with the dimension. This is just a reference value. For centrifugal pump is around 500 to 4,000. If you work in United States, the value is around 500 to 4,000, depend on operation. And these are the converter conversion unit. So if you convert NSD to NS, you use this constant value. Okay, so you calculate NS. Then if you work in the United States, you times 2733 to your answer. Then you'll get what they want. Specific speed is something you'll see this one also in the maintenance manual for the pump. So on the left is the efficiency. On the below axis is NS, is the specific speed given by the equation I show you on the screen here. Okay, so on this graph, you're having a 3 different pump. You have the centrifugal pump, you have a mixed flow, you have axial flow, right? And then you read this graph according to your operation. These two I introduced you just now, NS and SSD. So this is another chart that you extract from a book. This one is published by Hydraulic Institution. That they have combined all the design out there, give you the NSD, specific speed on the top, and then the specific speed NS at the bottom. So it's like a ruler. Okay, it's like a ruler. So the middle one is the type of the pump that meeting the NSD and also the NS. So for example, if you are calculating, after you calculate this, either the top one or the middle one, both works well. If you are work with NS, you start with the bottom axis. Let's say you get 0.2 in your calculation, you just project up. You will get the direct conversion into NS value, NSD, and you're having, there's a diagram in the middle, meaning your system is recommended to use the system on this diagram. The system is radial flow system, and the design can be what you see on the screen here. Okay, now for example, if you are if in your calculation you get 4 in your NS, meaning you use this calculation NS, you get 4, you just project up, you will get the conversion of your NSD that you communicate with your United States counterparts or United States colleagues or United States workers. So this value is the same as bottom. Top and bottom is actually the same, right? Then you will be hitting an axial flow diagram. So the system that you recommend for your company is you will be using axial flow pump and not radial flow pump. Okay, quite direct. Okay, just a test whether you know how to use this graph or not. Just a quick one. Okay, cool. This question is for you. If you are calculating your NS, if your NS value is 2.0, what kind of pump that you're going to use for your company? Cool, are you there?
Yeah.
Yeah. So in your calculation, if you get NS is 2.0, by looking at this table or this chart, what kind of pump that you are using?
5,000.
Yeah, 5,000 is NST. You convert this one to NST is 5,000. My question is what kind of pump that you're using? On your screen, we have 3 type of pump there.
Mixed flow.
Yes, correct. You're using mixed flow pump, and you can use accordingly. You can use impeller strut with the vent on this design and so on. Okay, good. Next question I'm going to ask Shirley. All right, Shirley, if you work in United States and you're calculating using NSD, the value is 2,000. What kind of pump that you're going to use?
Radial flow.
You're going to use radial. You are using this one, right? Okay. So this actually is between radial flow and mixed flow. Okay, you are in the middle. So you can use the mixture of either radial or radial flow or mixed flow. Both correct answer.
Oh, okay.
But it's just that in your pump, you need to select something when you have the cross section. You need to find something that the strut, the impeller is not higher than this height. It must be lower than the radial flow, and not too low until it meet the axial flow. So you just read from this diagram, and then you choose from the supplier the type of the pump that you use. Okay, surely you understand, right?
Yes, sir.
Okay, good. Okay, the next one, before I let you go for today, Raj, you there, right?
Yes, sir. Yes, sir.
Okay. So let's say you're calculating the NS, the dimensional specific heat. I give you an easy one. Okay. What happens if you get 7.0? What kind of pump that you're using?
So axial flow, sir.
Correct. The answer is axial flow. You move up from 7.0 and it's fall under axial flow. All right. So it's under here, axial flow. And if you need to communicate with the United States counterparts or your colleagues in United States, you from this table, you read up and then there's a value there. It's around 18,000 value for the specific speed. Okay, good. Dinesh back already. Let me see. Is Dinesh back?
Yes, sir. Just
Okay,
come back.
Dinesh, you're back. Okay, Dinesh, when you back, do you follow the NS and SST, the explanation?
Yeah, sir, slightly.
Slightly, yeah.
But
Okay,
I
just
don't understand. I
okay.
need to go back.
You view back the lecture video lah.
Yeah.
But from the question, when you join, do you listen to the question I asked from Ku?
No.
When you join, I'm asking who? Who is answering question?
Oh, this question, sir.
Yeah.
When asking Ku, yeah, I'm here.
You are there, right? So you
Yeah,
know how to use this table, right? Or this diagram. You know how to use, right?
Really, sir.
Yeah. So actually quite direct, right? So you either using NS or you're using NST. NST is in US, used in US only. So if you want, normally we'll use NS lah. It's a dimensionless parameter. You calculate this one, and then you get a value. So you have two axes here. One is for NST, one is for NS. Below one is NS. So let's say if you get NS 1.0, so you just read from NS, you go to the chart here, you find 1.0 here. Then you project up. Direct conversion for NST, you read from this. This is NST. You read the intersect, you get one value here. It's about 2,800 here. It's an equivalent value. It's like you convert if you're converting Malaysia ringgit to USD. Okay. Okay. Dinesh, you get it? The idea?
Yes, sir.
Then in the middle here is how you choose the pump. So you have three type of pump: radial flow, mixed flow, and axial flow. So in this here is very near to the mixed flow, but it's a combination of radial. So you look at the diagram here, is the differences is the impeller height, the hub, compared to the left hand side and right hand side diagram. Okay, all right. I hope you managed to get the idea. What else? Okay, I think we have two more slides. Another one is called suction speed. Just now is the specific speed. Okay, just now NS is a specific speed. Another parameter when you study about pump is suction speed, suction specific speed given by this equation. Right, you use omega, rotational speed, Q, volume flow rate, G, gravitational force, NPSH, we already covered in the previous lecture. So go ahead and listen back to the previous lecture. I explained about NPSH R. So you read this value and you manage to find suction specific speed. Okay, NPSH is required net positive suction head. The purpose of this parameter is to find the operating condition on the suction side of the pump. You know that pump have suction and the release output side. So this is suction side. Okay, this is the output. Okay, so this suction specific speed is very useful to determine parameter at your upstream. Yeah. Also, if you need to work in the US, United States, there's another dimensional suction specific speed given by this equation. All right. And then operational value is within 7,000 and 12,000. Normal is about 8,000. Okay, so this is the normal conversion value. If you want to convert dimensionless NS into NST if you work in United States, they use a dimensional form. Another one is flow coefficient. Flow coefficient give you by Q divided by omega D cube. They managed to help you. What is the purpose of this flow coefficient? Is to do pump scaling. What mean by pump scaling? It means that you manage to pick a pump that's suitable for another operation. For example, pump number 1 and pump number 2. And in the factory, you need to pump water. Let's say you need to pump water up to 100 meter. And another scenario is that you need to pump water a bit higher, maybe 200 meter. So by using this flow coefficient, you manage to find the more suitable cases for pump number 2. This pump number 1 is pump number 2. But let's say you're using the same company pump, then you can just scale up according to the scenario that you have. Okay, so these are the equation, and all these equations are found in the last chapter of 3179 when you do the dimensionless analysis. Okay, so these are the equation that we use. For the fan What mean by fan compared to pump? Fan is the speed is low. However, it moving in the volume of the gas is big compared to pump. Okay, how you define fan and pump? Fan, rotational speed of the pump of the fan is slow. Omega is low. However, the volume that generated by the fan, the volume generated by the fan is bigger compared to pump. So let's say this is a pump. Omega is higher. However, volume generated is low. Okay, so this is the parameter that we look at when we look at the parameter generated by the system. We can straight away tell whether this is a fan or this is a pump, or whether the pump is working or not. Okay. These are the differences between blowers, booster, exhaustor. So I already highlight the keyword for there. Blower located at the system entrance, meaning blower always, when you have a system, is always at the entrance. Exhaustor always at the exit. Booster at the middle of the system. Okay, what does it mean? It means, let's say you have a pipe system that transfer water. So blower always at the entrance. Let's say your Q is flowing from the bottom of the screen to the top. So the blower always at here, and exhaustor always at here, booster at here. Okay, this is the booster. Blower, booster, exhaustor. Okay. Yeah. So this is under fan. Under fan family, not pump. Sorry, it's under fan. So a fan that install at the entrance, we call it blower. A fan that we install at the exit, we call it exhaustor. A fan that we install at the middle of the system, we call it booster. Okay, so these are the name that we given to the fan. So if you work in the factory later on, and you need to fix one of the component inside your factory, make sure you go to the correct area. Okay, let's say the technical log in the company, he say, okay, blower has been damaged, you need to replace. So make sure you go to the entrance of the system to check and not go to the end, because the technical log is mentioning blower is damaged. So you need to check the fan at the entrance and not the exit. So if the technical log, in the technical log it mentioned booster is damaged, so you just need to check at the middle. So quite troublesome, especially when it become booster damage scenario, because inside the factory you have a loss of booster. So you need to check one by one. But however, when it comes to either blower or exhaustor, then it's much simpler case. You just go to either entrance for blower or exhaustor for the exit to just exchange the fan over there. Okay, so don't make a joke of your don't make a joke in your office later on. Make sure you are sensitive to the name of the fan. If your colleague mentioned blower, it means something at the entrance. If the colleague mentioned exhaustor, it means something at the entrance, at the exit. If the technical log or your colleague mentioned booster, it means something within the system. Okay, yeah. So these are the name, technical name. Yeah, another one, turbo machine is called compressor. Compressor, you need from the name itself means you compress something, means you change the density and pressure. Okay. So these are the formula we use for fan when you do calculation. And also there is for fan, we also have specific speed. Just now what I show you is a pump. Now we look at fan. So fan also has NS and also have NSD. Again, when you see SD, it means it's United States dimensional parameter. This is dimensionless without unit, NS. So you're using the formula here. Okay. And there are equation for the fan, we call it fan law. All these equation you can use for scaling, right? What I mean by scaling means, again, if you using a fan for one system, meaning on the graph, you can do the scaling. Scenario 1, scale to scenario 2. Then you get the reading from this equation. Okay. Now, for example, how do you use this equation? Let's say you have the Q, you have the omega, you have the D, and you need to design a new system with the same fan. You need to find the Q. Let's say you don't know the Q. You have the omega, you have the D of the system number 2. Then you use this scaling fan law. You can find the Q that you need. Okay. And the keyword for using fan law is they must be geometrical similar, meaning their design must be the same. Okay. The next one, turbine. Yeah, turbine is okay. We go for a few more slides, then we call it a day. Let me check how many slides we have. Okay, I think we stop here. We go for a short break for turbine. Okay, I think we have a few more slides to go. All right, let me stop the recording.